morning, everyone. Today we're going to start Chapter 7. Chapter 7 will be mainly concentrated on materials characterization. We have lots of materials that we cover when it comes to pavement design. We have multiple layers, and each layer need to be characterized and tested in order to know how strong it is to consider it in the pavement design procedure. So again, it's a very one of the most required steps that we need to do for any flexible or rigid pavement design. When it comes to flexible pavement design, we need to obtain mainly resilient modulus and Poisson's ratio for the subgrade, which is the soil layer, as well as the granular base. And also we need to get resilient modulus and Poisson's ratio for the asphalt layer. When it comes to the rigid pavement design, we are going to be looking into getting the concrete modulus of rupture, as well as the subgrade and the subbase support modulus, which is sometimes we call modulus of subgrade reaction, with the K value. So let's start with some of the basic parameters that we got to know even from physics, which is Poisson's ratio. Poisson's ratio, as we know, is a ratio of the lateral strain over the vertical strain. So when you apply a vertical stress or compressive stress, this sample will deform in the y direction. So it's going to compress. That compression, we call it again epsilon y. At the same time, this sample will bulge or will expand on the x direction, which we call this epsilon x. And that epsilon x is the difference in the x direction. That's the amount of strain, and if we divide the two of them together, one over the other, will give us a Poisson's ratio. So this is here a range for Poisson's ratio for different materials as well as different temperatures. So for the dense graded hot mix asphalt, and this is the top layer for the hot mix asphalt layer, it actually depends on the temperature. For the temperature that is less than 0 Fahrenheit, the typical range is 0.15, and as you could see, by the way, Poisson's ratio is a unitless ratio simply because it's a ratio of two strains. So coming back to the temperatures from 0 to 40, Poisson's ratio is 0.2, from 40 to 70 is 0.25, 70 to 100 is 0.35, 100 to 130 is 0.45, and anything else more higher than 130 Fahrenheit is 0.48. When it comes to the Portland cement concrete, the range is pretty consistent. It's somewhere between 0.15 and 0.25. Typically, we consider it as 0.2, and it actually doesn't change by changing temperature. For other materials such as unbound materials, when I say unbound materials, I'm talking mainly about soils, different types of soil. For example, clay, saturated materials, typically the Poisson's ratio is 0.45, sandy clay is 0.25, silt is 0.325, all the way to bedrock, which is very stiff material. That's why the Poisson's ratio will be 0.25, getting very close to the concrete material actually. For bedrock, again, it really depends if it's solid or massive or continuous bedrock, so it's 0.15, and if it's highly fractured or weathered bedrock, it's 0.3. That's why we have this range from 0.1 to 0.4. Another a little bit highly sophisticated test compared to Poisson's ratio is what we call the resilience modulus. Resilience modulus is basically the same as elastic modulus, but it's under repeated load. As we got to know that any material that we need to test in pavement, it has to be done on a repeated scheme in order to replicate traffic loading. So since we have traffic loading, it's as a repetitive loading and it comes and goes, we have to have same simulation when in the lab in order to characterize any any subgrade or unbound material in the right way. So this is here a major schematic for what happened during the test. So the test it's basically it's a loading test, which is this line right here, and then there is and there is also again we have unloading. Let me here see if I can write this down. So this is here the beginning of the test, and then we load the test. So it goes up, we load the test, and then we unload the sample. So why we load it? We load it because this is now when there is a traffic movement on that point. And then when we unload it, so the sample will relax. So it's gonna go down this way. But guess what? It doesn't go to the original point. There will be something called accumulated strain, plastic strain. Therefore, this is here. It's an accumulated plastic strain. It's not gonna get to the original point anymore. While at least from this point to this point, we call the elastic strain. So the soil would recover that much, which is quite a bit. But the total strain, which is from here all the way to here, this is the total strain, which is the elastic strain plus the plastic strain. So from this point, we do the second loading. We start from here and we load again all the way to here, and then we unload again. So it goes all the way to here, and that's another point. So every time we load the sample, we're accumulating some plastic strain with time, while we still have some elastic strain, which is what sometimes we call a recoverable strain. So this is here epsilon r. This is the what we call the recoverable strain, which give us an idea how much plasticity that does this sample or does this material really has. So based on this test, we're interested to get the resilient modulus, which is MR. The resilient modulus is typically defined by based on mainly on the recoverable strain under repeated axial loading. That's why you would see this is sigma D. This is the deviator stress. This is the amount of stress that we apply over epsilon R, which is this is what we talked about here. This is epsilon r here, the amount of recoverable strain. So it really we're interested to know how much does this material have the capability to recover after a traffic loading. And that's why this ratio comes into place, which is sigma d over epsilon r. So how about the type of the test and the duration of the loading? So the type of the test, as I mentioned before, is a repeated load test that should try as much as we can to simulate the type and duration of the loading occurring in the field, the traffic loading in the field. So when a wheel load is at a considerable distance from a given point, that means the stress is equal to zero. So the wheel is far away from certain point of interest. So therefore, the stress has to be zero. And then when the load is above the point, this is where the stress is maximum at that point of interest. Therefore, we try to assume that there is a stress pulse. Typically, it's positive sinusoidal or triangular loading. What does that mean, sinusoidal loading? Let me try to draw it here, sinusoidal loading, something again like this. So we apply the load, we have a rest time, we apply the load, and we have a rest time, and so on and so forth. This is sinusoidal. It's not really a pointy loading. It's gradual. So from zero right here and go all the way up to the maximum and gradually goes back to zero. And then this is here we have a rest time, and then another loading will start. A triangular loading is similar, but the way it's done, again, it's very sharp. We have and then we have here a rest time, and then we start again. So again, those are the two schematic that sometimes we use, but we tend to use the sinusoidal loading more than triangular loading. Or sometimes we do a square wave vertical pulse, again, not something like this. So it starts from zero, something like that. So there is again different types. Again, forgive my drawing. Again, it's not the best. I'm using the mouse here but again, you got the point. The duration period of each one of these loading, it actually depends on the vehicle speed as well as the depth of the point of interest below the pavement surface. So you may wonder again how long that this loading last. Again, it depends on the speed. If the vehicle speed is low, therefore the loading will stay longer applied at that specific point. If the speed is high, then the loading time would be very small. So Barksdale in 1971, he came up with this very important graph that actually correlate two things to the equivalent pulse time. Because again, to run any test like what we've shown you here, we need to know how long does this loading period should be designed for. And as we said here, it mainly depends on the vehicle speed as well as the depth of the pavement of the point of the pavement surface. So we came up with this graph. As you can see in the x-axis, we have the depth below the pavement surface. So we have from 0 all the way to 28 inches. And then in the y direction, we have the equivalent pulse time. And each one of these lines represent a speed or a velocity. So a speed of 1 miles per hour typically represents any condition at a parking lot. And we have a speed of 15 miles per hour, 30 miles per hour, all the way to 45 miles per hour. We also have two lines, one sinusoidal and one for triangle. Sinusoidal is a continuous line, and triangular is the dashed line. So this here gives us an idea if I want to run any test, whether sinusoidal or triangular, what should be the equivalent pulse time. For example, let's say I have a roadway that the velocity is actually 30 miles per hour, and I'm interested to simulate this test at a depth of let's see 8 inches. So the depth is 8 inches. And I want to do a sinusoidal test. So what we do here, we look into the 30 miles per hour. This is the two groups for 30 miles per hour. I'm interested in the sinusoidal, which is a continuous line. And I'm gonna go now with, so this is the 30. So I need to pick this line right here. And it's 8 inch. So I'm gonna go up all the way to here. Then I'm gonna go now horizontally to pick what should be my equivalent pulse. So here we have 0.01 and here we have 1. So this is here 0.02, 0.03, 0.04. So this is roughly 0.05 seconds. So 0.05 seconds. This is so if I go now to the sinusoidal load, what I'm trying to say here, I need to design the loading criteria. Let me draw it right here. So the sinusoidal loading, as I told you, it's a loading, and then we have a rest time. But the length of that loading would be 0.05 seconds. And again, the list goes on and you can pick any combination on how to use this graph. The duration of the loading for determining the residual modulus under repeated loading can be again selected from the graph that I showed you before. Mainly if it's again from Braxdale Haversine loading or sinusoidal, they're similar. Or there is another one for MacLean's square wave loading, but as I told you, the square wave loading is not that frequently used compared to the other one, so that's why I would still recommend you to look into the Barksdale loading mainly. For lab testing, if you wonder what's the typical loading that we do in lab, do we really look into each speed? Yes, if it's specific location, we look into the speed and try to use again Barksdale graph, but if there is not much information there, typically the typical load setting that we typically use is the load duration is 0.1 second and the rest period is 0.9 seconds. 0.1 second represent 10 hertz loading, so it's pretty fast loading, especially for designing highways above 40, 50, 60 miles per hour. The load duration, as you could see from the figure, the load duration itself has very little effect on the residual modulus of granular materials. It's different than what we're going to see in the next lecture. What's the impact of the low duration on a hot mix asphalt layer? But for the resilient models, it has very minimal effect. Some of There is some effect, especially on the fine grained soils, where because there is moisture content there, but when it comes to the coarse grained soils, not much effect. But of course, there is, as I told you, there is a considerable effect on bituminous materials, which we're going to discuss later on. The rest period effect for some grain materials is not known, probably is insignificant, but again, it's going to be very significant for bituminous materials later on. Now let's move on to another type of testing. This is here for flexible pavement for unbound bases and subgrades. So for a new design, we typically also do granular material and fine soils. We do resilient modulus. We can obtain the resilient modulus from different testing. The concept that I just showed you is this is the concept of a resilient modulus in general. We can apply the sinusoidal loading or triangular loading using all these types of testing that we're going to go through. The very first one, which is again very related to what we just introduced you to, is the repeated load triaxial, which is RLT. It has an AASHTO standard, which is T307. And then afterwards, if this is the most sophisticated test, we're gonna go from the most sophisticated one to the simplest one. So the first one is the repeated load triaxial, and then we're gonna have the California bearing ratio test (CBR), which also has an AASHTO standard of T193, and then we have the resistance value or R value, which has an AASHTO of T190. And if you can't do any of these tests, we can go back and use the AASHTO layer coefficient tables or figures that we're going to introduce you to them towards the end of this lecture. So let's start with the first one. For the repeated load triaxial test, the resilient modulus, which is MR, for any subgrade or base material is based on this AASHTO T307. And again, we're trying here to estimate what will be the modulus of elasticity for this material. So the loading scheme, as I mentioned to you before, is 0.1 second loading pulse, and then we have a 0.9 second rest period. Typically, we do this test in a way that we compress the sample by air or liquid. Why we do this? We're trying to simulate what's going on in the field. If you take a sample from the soil, which is unconfined, we take it from the field and we test it in the lab without any confinement. We typically underestimate the strength of the soil comparing it if we tested it in the field, simply because the sample in the field is very confined by other particles, so it gains strength by that confinement. So in order to simulate that confinement level in the field, we typically again compress the sample with air or with liquid with water while we test it. So the way we do it here, we apply again a repeated axial cyclic stress, which is the sigma d on a fixed magnitude, so it's a fixed loading, and the load duration again is 0.1 second. The cyclic duration is applied to a cylindrical sample. Typically, again, we take a cylindrical sample from the field, or we manufacture it in the lab, and that's what we apply the testing to. While the specimen is subjected to a dynamic cyclic testing, which is again sigma d, we also are subjected to a static confining stress, which I told you before. Again, we have to apply a constant amount of confinement stress to simulate the confinement situation that we see in the field. And again, this is provided by a triaxial pressure chamber. So this is here a schematic of what's going on. This is the sample right here. This is a soil sample, and what we do, as you can see here, the lab worker here, he's preparing to cover the sample with a rubber membrane. The rubber membrane, this is here where we apply confinement on the sample. So the amount of stresses on the sample is as follows. Sigma C, this is the confining pressure. So sigma C is constant, as you could see from all over. So we have sigma C from the side, sigma C from the top. So it's a constant amount of pressure applied to the sample. On top of this, we apply, while we're loading the sample, we apply it we load it with a cyclic deviator stress, sigma D. So going back to foundation or geotechnical engineering, so sigma 3 in this case, which is going to be sigma C, and sigma 1 will be sigma D plus sigma C. So sigma 3, which is typically on the side, so this is here total, this is sigma 3, which is typically only the equal to the sigma C, and sigma 1, this is here sigma 1, is going to be the summation of both sigma C, which is the confinement stress, plus sigma D, which is the deviator or deviatoric stress. So we could tell here that the sigma D, for example, if I want to just put it on one side, it's going to be sigma 1 minus sigma 3. And again, we can have compressed air or compressed liquid to simulate confinement. The specimen size depends actually on the material type. If we have a fine material, fine soil, we don't need to have a big sample. But if we have a coarse material, we will have to have a bigger size. This is here another true picture of the sample while it's inside the machine. So this is the specimen here is enclosed vertically by a thin rubber membrane on both and on both ends we have rigid surfaces or platens to apply the load on them. This here is schematic to show you all the components that's needed to run the test. So during the test, this is here the repeated load triaxial loading scheme. So we apply typically again we have this constant stress, which is the confinement stress. So we start from again not zero. Again, this is the constant stress is gonna be there across the board, and then we start loading. This is here the deviatoric stress until we reach a maximum value, and then we go down. So this is here, which is a 0.1 second loading, and then I have from here all the way to here. This is a 0.9 second unloading, and then I start the second cycle. While I'm doing this, this is the applied stress. I'm gonna measure the applied strain. Once we apply the stress, as you could see here from the top part, we are. Let me see here to draw this to you. So once we apply the stress, we're gonna now measure the strain. So this is what's applied, but this is what's measured. So what we're gonna measure? We're gonna have also a constant strain similar to the constant stress, because once we have a constant stress, that means we're gonna have a permanent amount of strain according to that. And then once I apply now the deviator stress, I'm gonna start to see that we are measuring now some strain that correspond to the amount of stress applied. And again, we see it applied at 0.1 second, and then we're going to have a 0.9 second unloading, and we see it again, and this keep repeating. So, in general, the total resilient modulus, which is the recoverable axial deformation, and this is again what I mentioned to you earlier, the recoverable strain, this is what we're looking into. So the resilient modulus, which is MR, is basically will be sigma D, the deviatoric stress, over the resilient or recoverable strain, which is measured again during the testing, and it's used to calculate the resilient modulus using again this equation. So what we do here, we don't apply this type of loading just once. We apply it different times. We apply different schematics in order to have a good understanding what will be the resilient modulus, a good representation from this sample. So what we do, we apply various combinations of confining pressure as well as deviator stresses. Sometimes again we have a set of confinement pressure and we apply various deviator stresses for every 200 cycles. For example, we typically set the sigma C, which is sigma 3, to 20 psi, and then I apply sigma D of 1 psi for 200 cycles, and then I apply 2 psi for 200 cycles, and I apply 5 psi with 200 cycles all the way to 20 psi while the sigma C is constant. and then sometimes I reduce again sigma 3 and I apply the same sigma d again. So sometimes so this sigma 3 here we reduce it, instead of 20 we do 10 psi, and then we apply the same sigma d combination from 1 to 20, and then we do 5, and then so it's a big test and it's time consuming, and this is here what I want to show you. After we do all these types of testing, then actually what we do, we plot the relationship between the resilience modulus that was measured versus theta, which is the stress invariance. So the relationship that we're looking to achieve here to know what's the resilience modulus is the resilience modulus is equal to K1 times theta to the power K2. So MR, we know what's MR, this is the resilience modulus. And by the way, this relationship is for the granular materials. So K1 and K2, those are experimentally derived constant, which we're gonna get to know how can we obtain them. But theta, I want to stress on this, theta is actually sigma 1 plus sigma 2 plus sigma 3. This is here the stress invariant. And again, K1 and K2 will be obtained from the graph. So what happens is we typically plot the resilience modulus that we obtained versus the theta on a log scale. And then typically what we see that there will be measured data points from the test along this line here, and then we're gonna do a regression analysis to obtain for us what's the intercept and what's the slope. The intercept of this relationship here, the y-intercept, would be the log of K1. So this is what's gonna give us the idea for K1, and the slope of this relationship would be the K2. The slope would be the K2. And we're going to go through an example to explain for you how to get those. So let's have your example, which is from your textbook, example 7.2. It shows this table shows the results of the resilience modulus test on a granular material. The distance between the LVDT, this is the strain. Basically, it's a strain gauge sample that we put on the sample to measure the amount of deflection or deformation. So the distance is 4 inches. Why we need this? Because to get the strain. Remember, the strain is basically, if you remember again, the strain is delta L over L. Delta L over L. So now by knowing that the original distance is 4 inches, this is the L. And then once we get now the difference in delta L, this is where we get the full strain. The average recoverable deformation is measured by the two LVDTs after 200 repetitions of each deviatoric stress are shown in the table 7.2. Determine the nonlinear coefficient of K1 and K2. Typically, we don't ask what's the resilience modulus. We're very interested in K1 and K2. Why is this? Because if I really get to know what's K1 and what is K2, I'll be able to get what's the resilience modulus. So let's show you now the graph here. As I showed you, so let's see here. That's okay. So this table here shows you the confining pressure, sigma 3, and then this is the deviator stress, sigma d. This is what's actually applied. We apply, and then this is what's measured, the recoverable deformation, and then this is the recoverable strain, and then this is the resilience modulus, and then this is the stress invariant. So let's understand this table. This is very important to understand. So first we apply confined pressure of 20 psi. So this is constant. This is what we confine the sample with. Then for the first 200 cycles we apply a deviator stress equal to 1 psi. So if I draw the sample here, a cylindrical sample, so the confinement pressure across the board is 20 psi, and then on top here the deviator stress is 1 psi. So my question to you is, let's jump to the last column here, the stress invariant, which is 61. How can I get what is the stress invariant 61? theta, which is, as you remember here, theta is sigma 1 plus sigma 2 plus sigma 3. So how did they get 61? Which is right here. 61 is basically 20 plus 20 plus 20, 20 plus 20 plus 21. Why is this? Because theta is sigma 1 plus sigma 2 plus sigma 3. So if you recall from here all the way to here, so sigma 1 is sigma d plus sigma c. So sigma d in this case was 1 plus sigma c, which is 20. And that's why from the top it's going to always be 21. From the side, this is here sigma 3 is 20. And from the other dimension here, the other 3D here pointing inside the slide, this is another 20. So this is 20 and this is 20, but from the top here it's actually 20 plus 1. So it's 20 plus 20 plus 21, that is 61. I hope this makes sense. So coming back to here, that's why we see 61. So we apply 20 all over the sample, 20 from here, 20 from there, and then here we have 21, and this is why we arrived at 61. Next, we need to understand this column here. The column here, recoverable deformation, this is what we measure and during the sample, during the test, I mean. So this is measured, nothing really fancy about it. So this will be provided to you. What you need to measure or what you need to calculate is the recoverable strain. Recoverable strain, which is 0.066 here, it came from this equation right here. This is the strain. The strain is equal to delta L over L. So what do you need to do? Delta L, which is the deformation, which is 0.264. If you divide 0.264 over 4 inches, which is the L, the length of the sample, the original length, you're going to be able to get this one here. So this is really a 0.264 over 4 inches. You're going to be able to get the strain, which is 0.066. Then the resilient modulus. How can we get the resilient modulus for this very first line? Resilient modulus, if you recall, go back to here. Again, this is resilient modulus, sigma d over epsilon r. The deviatoric stress. How can we define the deviatoric stress? It's right here. Sigma d, this is the cyclic deviatoric stress, which is in this case it was 1 psi. So if I go to this equation, it's going to be equal to 1 psi over epsilon r. Epsilon r, this is what we calculated previously, so which is this column right here. This is here epsilon r, as you could see. So if I divide epsilon r, if I divide the 1 psi over 0.066, and I'm gonna apply it here using my cell phone calculator right there. So I'm gonna divide again the stress, which is 1 over 0.066. I'll be able to get 15.2. I have it here. So that is 15.2, which is why it's times 10 to the power 3, by the way, because this number is very small. This is in 0.001 inch. So in reality, if you really want to do it in the right way, so if you divide mr, so mr is equal to, as I showed you here, mr is 1 psi over epsilon r. Epsilon r in reality, as it says here, this is 0.066 times 10 to the power 3, and that's why you're going to end up with 15.2 times 1000 psi. So once you do this, you need now to do it for across the board. So 20. Now once we do for the first 200 cycles, we're going to do 1 psi. You're going to get this amount of strain. I mean deflection. You're going to divide it by 4 inches to get 0.066 times 10 to the power minus 3. Resilient modulus is simply the deviator stress over the strain to get this number. Then we run the same test for 200 cycles at 20 psi confining stress plus a deviator stress of 2. So what does that mean? I'm gonna draw the same sample here. We're gonna have 20 on this side, 20 on this side, but guess what? Now we're gonna have 22 on the top. So we're gonna have 20 plus 20 plus 22, and that's why we have 62 as a stress invariant. This is gonna be measured. We get the recoverable strain by dividing by the 0.496 times 0.001 over the 4 inches to get 0.124, and then the MR resilient modulus again will be the deviator stress over the resilient the recoverable strain. So in this case would be 2 over 0.124 times 10 to the power minus 3 to get the 16.1 times 10 to the power 3. You're going to keep doing the whole thing for all the numbers, because now once we're done with the 20, so we do 20 at 1, we do 20 at 2, 20 at 5, all the way 20 psi with 20 psi deviator stress, and then we shift to 15, and then we go to 5, all the way to 1, 1 with 1, 1 with 2, all the way to 1 with 10. Once we come up with all, we finish this table, we're going to end up with two major columns that we need to plot in order to get K1 and K2, which is this column right here, the resilient modulus versus the stress invariant. Remember this relationship here? We have the stress invariant in the x direction and the x axis, and the resilient modulus is on the y axis. So once we have these two columns, the last two columns of this table will be used to plot this graph. So here we have in the x-axis we have the stress invariant, which was the last column, and then on the y-axis we have the resilient modulus, which is on the y-axis. So once you plot these numbers, we're gonna come up with this relationship. And now what we need to do, you're gonna be able now to obtain the K1 and K2. So the K1 would be this value. Oh, well, that's just making sure. So the K1, so this is going to be the log of K1, or since you're plotting it on a log scale, so you don't need to do that. All what you need to know, again, this is the K1 value, and the slope of this graph here would be the K2. So this is K2, and this is K1. And please again review the example to follow the exact numbers for K1 and K2 for this material. For fine materials, so far what we covered for granular or coarse material. For fine materials, the relationship is a little bit more interesting. We have the resilient modulus, we have sigma d. We don't have the stress invariance, so we plot this based on sigma d versus mr. So what we have here, we typically have more than one relationship. We start with the maximum number for the resilient modulus. We have minimum number for the resilient modulus, and then we have two curves or two lines here. The first line was defined by a slope of K3 and an intercept of K1, and we have K2 and K4. So same thing, we're going to do the same exact type of testing. This is example 7.3. We have resilient modulus test. That was tests, actually it's multiple tests, were done on fine grain material. The distance between the LVT is also 4 inches. The average recoverable deformation measured by the two LVTs after 200 repetitions is in the table, which I'm going to show you in a little bit. And then the uncovered compressive strength of the soil is 15.5. I'm going to get to know why we use this. And then we need to determine K1, K2, K3, K4, and the maximum minimum resilient modulus. So we have the table here. So let's see what we have in this table. Same thing, nothing changed. We have here deviator stress 1, 2, 4, 8, and 10. This is the applied stress, and then we have the confining stress sigma 3, and then we have recoverable deformation. This is what we measure during the test, and this is what we get to obtain recoverable strain, which is the recoverable deformation over 4 inches. And then we get the resilient modulus, which is again resilient modulus is sigma d over epsilon r, which is sigma d, which is in this case the first column, over the recoverable strain, which is this column right here. Once we do this, we also need to plot them. So here, what I'm showing you, we are plotting the deviator stress, which is sigma d, and the x-axis over the Resident modulus, which is on the y-axis. So once we plot the relationship, this time actually it's not on a log scale; it's on a regular scale. We set the maximum value, which is right here. Typically, again, it's an engineering judgment actually. So if you ask me how to obtain the exact number, again, there is not specific number or specific way of doing it, but typically, again, we try to draw a number here. Typically, again, there's not specific one, but that's where we draw the line for this case. But what I'm really interested in for you to obtain is the relationship, which is K1, K2, K3, K4. So we could see that there are some points here, a cloud of data points that formulate this line that has certain slope, which is K3, and it has and then this cloud of data, it's formulating another type of line. It has its own slope, which is K4, and then once we intercept these two lines together, this point right here, the x-axis of this, the x-coordinate of this point is basically K1, which is 5600 and then the K2 is 5.5.2, which is all the way to here. Another equation, so this is another equation here for the repeated load triaxial, is the Resident modulus. This is, we actually came up from another project. The project is NCHRP 128A. You can look it up, there is a whole report about it. We came up with this equation. We're not going to indulge on it that much, but I just wanted to give it to you and show it to you in case you see it later on. K1, K2, K3, these are again coefficients we get from regression analysis, but what's more important is the other factors. PA, for example, PA is the normalizing stress, which is atmospheric pressure. Theta, this is the bulk stress, which is the sum of the principal stresses. Tau octahedral, this is the octahedral shear stress, which is 1/3 of the square root of sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared. So this equation actually it estimates for us the Resident modulus for both materials together. So instead of having two relationships like what I showed you before, one for granular based materials and one for fine grained materials, this equation applies for both. So, but there is portion of this equation is highly dependent on the bulk confining stress. So it has a stiffening term, which is K2, that's higher or equal to 0. And as I said, it's dominates for coarse granular soils like base and subbase. This portion of the equation is highly dominated and characterize the shear or deviatoric stress. So it has a softening term, K3 is less or equal to 0, this one right here, and it dominates for fine-grained soil or subgrade. Again, I just wanted to throw it to you out there just so you are familiar with this equation based on this project. Moving on now to another test, which we call a CBR test, California bearing ratio. It was developed actually in California Division of Highways in 1930, and it was subsequently adopted by lots of state DOTs and counties and even countries outside the US until it's used by federal agencies in the US as well as overseas. It's a very simple test, relatively speaking, compared to the triaxial test that we just covered. The test compares actually the bearing capacity of a material that is well graded crushed stone to any sample that we are that we're facing in the field. So this sample or this crushed stone that was tested in California is a high quality crushed stone material, which should have a CBR of 100%. So any material later on that we test, we're going to compare it, we're going to have a ratio between the test that we do in the field versus this perfectly crushed stone material that we tested in California, and that ratio will give us an indication how strong or how weak this material is. So basically the test is being done by applying a load to a small penetration piston, and the rate we apply on this sample is 1.3 millimeter, which is 0.05 inches per minute, and we keep recording the total load at penetration ranges actually from 0.025 inches all the way to 0.3 inches. Once we do this, we're going to develop again a ratio between X and Y. X, this is the unit load on the piston for 0.1 inch or 0.2 inch penetration, and the Y value is the standard unit load for well-graded crushed stone at 0.1 inch, which is known to be 6.9 megapascals, or at 0.2 inch penetration, which is 10.3 megapascals. So as I said, it's a ratio of loading. So I'm gonna keep applying compressive strength until I reach 0.1 inch deformation, and I'm gonna measure that load. So that load, let's say again, it's certain amount of megapascals. I'm gonna divide it by the penetration for that perfect material that was tested in California at 0.1 inch. That was 6.9. If I divide these two numbers and multiply them by 100, I'm gonna get the CBR as a percentage. This is here the machine, how it looks like, the California bearing ratio. It has an AASHTO standard, very well defined in AASHTO T193. And again, we apply the rate, using a rate of deformation equal to 0.05 inches per minute. So it's a continuous monotonic compressive test until the sample reach again 0.1 inch penetration or 0.2 inch penetration. This is here just to give you an idea of the CBR range that we typically use depending on the soil type. So if we have a coarse grained soil, well-graded, for example, well-graded soil, we have a CBR value that can range from 40 to 80. If we have very silty clay, which is one of the worst case scenarios, you can have a CBR as low as 5 to 20 CBR, which is very weak material. For fine grained materials, again, we start from ML soil all the way to OH, and again, the CBR range can go from 15 all the way to, I've seen sometimes CBR of 2 or 3, which means again very, very weak soil, which need to be stabilized or sometimes replaced before we start paving the road. The question is, how can we convert the CBR value to resilient models? Because any of the pavement engineering software that we use to design pavement design, it requires an MR value, it doesn't require a CBR value. So this is the equation that we typically use to convert the CBR to a resilient model. So CBR to the power 0.64 times 2555 to get us the resilient modulus and PSI. A third test that we also do, it's called R value. It's an AASHTO standard, the T190. Actually, it expresses the material's resistance to deformation as a function of the ratio of the transmitted lateral pressure to applied vertical pressure. So we apply vertical pressure and we measure how much lateral pressure is being measured. It was actually developed by VM and Carmody of the California Division of the Highways also, and it was first reported in the late 1940s. So what is this all about is, again, we prepare a sample. So it's a lab prepared sample that are fabricated to a certain moisture and density condition that represent the worst possible in situ condition of a compacted subgrade in the field. The R value typically is calculated from the ratio, again, of the applied vertical pressure to developed lateral pressure. and it's some sort of a measure of the material's resistance to plastic flow, if you will. So this is here a schematic of the sample. So we have a sample in the middle, and then we have a base, metal base, and we have a testing head, and then the testing apparatus that's used in this test we call the stabilizer. We have a pressure gauge to measure again the pressure. We have a rubber membrane across the sample, and then we have a fluid under pressure to give us an indication of the lateral pressure that's being generated. So this is the real sample here, the real equipment. The sample is in the middle. We apply again vertical pressure, and then we measure the horizontal pressure as well as displacement. This displacement actually is displacement of stabilizer fluid necessary to increase the horizontal pressure. So what happens here is we have the sample, the diameter is 4 inches and the height is 4.5 inches, and then we apply known vertical pressure, which is PV. And then so let's say here I have three columns of data. So we have PV, which is the vertical pressure, and then I have pH. This is the horizontal pressure, and then we have the last column is the displacement of this stabilizer fluid necessary to increase the horizontal pressure. This is D, or sometimes called D2. So if we have these three columns, we're going to be able to get the R value. How can I get the R value? Is 100 minus 100 over 2.5 over D2 times PV over pH minus 1, all this plus 1. So PV, this is easy. PV is the vertical pressure. So we're going to keep, typically the tests start from a low vertical pressure until we reach a vertical pressure of 160. Let's say here we start with 10, 20, we reach again all the way to 160. 100 again, excuse my use of the mouse here. So this is the PV. While we apply the vertical pressure, we have control to measure what will be the generated horizontal pressure. So this is going to be measured, and then also we have the D2, the amount of displacement. So the PV in this equation has to be 160. So we run the test until we reach 160. So the PV here is known. pH, this is the horizontal pressure at a PV 160. So we keep applying the pressure until we reach a vertical pressure equal to 160, and the corresponding horizontal pressure, that would be the pH that we're going to plug into this equation. For D2, actually this is the difference, the displacement of sublimator fluid necessary to increase the horizontal pressure from 5 to 100. So this is actually D2 is the difference between two different displacements at two different horizontal pressures. So once I look into the horizontal pressure that's equal to 5, and I look into the horizontal pressure that was generated that's equal to 100, and D2 basically will be the difference in the displacement between these two corresponding numbers. So at 100 and at 5, I subtract the 2 from each other to get the D2. So once I get D2, and I know PV is equal to 160, I know pH is the corresponding horizontal pressure at PV equal to 160, I'll be able to get the R value. Typical R values, numbers for well-graded, dense graded crushed stones is 80 plus. For MH cells is somewhere between 15 and 30. And the bigger question here is how can we convert the R value to resilient modulus to use any payment software? Where there are multiple equations. These are the two famous ones, but I recommend you, this is the updated equation that we typically use nowadays. Resilient modulus is equal to 145 times 10 to the power 0.147 times R value plus 1.23. It's a very empirical equation, as you could tell, but this is basically based on multiple data points that was measured over the years to correlate the R value to the resilient modulus, and that is the equation that I recommend you to use. Last thing here I want to mention before I let you go for this lecture is in case you can't do triaxial test, you cannot do CBR, neither an R value test. There is also the H2O layer coefficients that were determined from the row test based on the H2O tests. So those are basically from correlations from material properties that was developed back in the 90s. It's recommended that the layer coefficient be based on the resilient modulus. So for example, if I get to know what's the layer coefficient from the Ashtaroth test, I divide it by 0.14 times 30,000 to get the MR value. And again, what's AI? This is the pavement relative quality as a structural unit related to the resilient modulus. So there is lots of these figures in your textbook. So for base layers, and your textbook page 296, figure 715. For the sub base, we have the textbook page 269, but now figure 7.16, and for the subgrade, it's figure 7.10. This is here an example of one of these figures, figure 2.6. So again, this is not from your textbook, but the textbook is there, you have them, but this is from another source similar to them, but this is for untreated base coefficient A2. For untreated bases, that means it's just a crushed aggregate basis. This is here CBR value, this is R value, this is the Texas triaxial, which is another test very similar to the R value, and then here we have the modulus value or the structural coefficient A2. So it really depends. If you have a C-bar value, you can use this graph to relate C-bar directly to the modulus. If you have an R value, you can do that. Or if you don't have any of those, but you just have the structural coefficient A2, you can also correlate it to the modulus value right there. There's another one here for ATB. This is treated bases. Basically, we have the same thing here, the structural coefficient A2. And we have here the Marshall stability. There's another test we didn't mention, it's not highly used nowadays, but if you have A2, the structural number, you can go directly to get the modulus, which is in this column right here. CTB, this is so this is here ATB. This is the for aggregate treated bases. This is here cement treated bases. So for cement treated bases, we have again A2, which is the structure coefficient versus the modulus in this this graph right here. We have a sub-base layer coefficient A3. So A3, this is any subgrade that we may face. Again, if I know the CBR, if I know R value or triaxial, or again, if I don't need to do any of these tests, I can just know what's the A3 for this sample. I go all the way and get the modulus value. So with this, I think again we finished this part of the of this chapter where we talked about all types of testing that we can do for unbound materials, including base, sub-base, and subgrades. We can go as sophisticated as triaxial test, or we can do something in between, CBR test or an R value test. And if we can't do any of these, we can come up with a correlation between the layer coefficient from A1. So from A1 or AI using this equation all the way to using these graphs for specific types of bases and sub-bases A2 all the way to A3, which is a sub-base layer coefficient. With that, again, we finish this part, and I will see you next time. Bye bye.